Welcome to Beyond BIM. In today's episode, we explore digital twins in more depth. I spoke with a fellow University of Cambridge alumni, Dr. Eva Agapaki. Eva is currently working at PTC as innovation lead and senior software developer. There, she applies cutting-edge computer vision and deep learning algorithms in engineering applications, most notably in the field of digital twinning. Prior to joining PTC, she completed a PhD degree in the engineering department here at Cambridge. Her area of expertise is solving tedious engineering tasks with innovative technologies with less time and effort. But she also says that she enjoys teaching, especially the future generation of engineers, namely by combining knowledge from the computer science field. We discuss her most recent innovative research on systems called CLOI-NET and what is needed for making digital twinning of complex infrastructure a possibility. Without further ado, let's hear what Eva has to say about the latest research developments in digital twinning of geometry. Eva, could you tell our listeners a little bit more about yourself and what led you to your current role as innovation lead at PTC?
So I started my career in civil engineering. I graduated from the University of Patras in Greece, where I come from actually. And I started there being very curious about research, and I was working at the time on mathematical models of soil structure interaction. And that's what got me interested into specializing more in geotechnical earthquake engineering. And that's how I got my master's at UCLA. On how to understand how structures and soil interact. So that there, I would say it was my first interaction with a different setting of digital twins, which was more in scaled down replicas of underground structures. Since we were working on centrifuge experiments for one of my projects there, and afterwards. From these experiences, I really wanted to contribute more into research, and I wanted to have like an innovative and big impact in the industry as well. So I found that industry-sponsored PhD program by Aviva MBP, and it was in the Construction Information Technology Lab at the University of Cambridge. That's how I got into Cambridge in the UK, on the other side of the world. And the project was really fascinating from the beginning. So in a nutshell, the goal was to automate the 3D modeling of existing industrial factories. And I knew from the beginning that it was going to be a very challenging and demanding project, especially since I was coming from a civil engineering background with very little interaction with computer science and coding at the time. But I wasn't intimidated from that factor. So I started my PhD in 2016. It was a steep learning curve. I need to be honest about that. But at the same time, it was very exciting to learn about computer vision and machine learning and also innovate on that. It was exactly around that time, actually, that the first deep learning algorithms, particularly in processing 3D data, were invented from laser scanners. And then my advisor mentioned about the scholarship funded by the National Academy of Engineering in the US for research projects that have the potential to solve one of the 14 grand challenges in engineering. So I applied for it, my proposal was accepted, and that's how I came to the other Cambridge in the US as a scholar at MIT. in the computer science department. That really helped to combine both worlds in such an interdisciplinary problem that I wanted to solve. After that, I graduated in 3.5 years, so last spring actually. And then I was exploring the commercialization of my research. So I started a startup. I interviewed many industry experts. I worked on some case studies, and it was going really well, actually. But it was the time that the pandemic started, and I was offered a software development position at BDC. And it was very well aligned with my research goals and the digital twins of spaces. So that's how it started. And then on the way, I took the initiative through an internal innovation program that we have at BDC to start my own team, where I'm exploring cognitive services and new technologies for the recognition of industrial objects.
That sounds like quite a journey from starting out to learning how to code and now leading your own team to innovate within that domain. So, like you mentioned, digital twins is obviously very much interlinked with this area of innovation that you delved into. So we've heard a lot about the proliferation of digital twins, but what does this presently look like in infrastructure?
Digital twins in infrastructure is actually an integration platform where multiple data management systems would come into play. So like IoT data systems, BIM models, and temperature, other sensors that would provide information about the current state of a facility. This is a really hot topic in the construction industry recently. And in terms of the design and construction of new buildings, there has been actually a lot of improvement and so many new advancements in the past years. So the majority of buildings and facilities, I would say, they need to have their own digital twin copy, and there are lots of initiatives here in the US and the UK as well, in terms of even the government urging to have those requirements at first hand. Similar for other types of infrastructure, there are lots of improvements in terms of digital twins for bridges, for tunnels and roadways that are coming up, but are more research focused. And there have been startups that have emerged in many of these domains. On the other side, digital twinning on existing infrastructure is still a manual process. So this is the challenge nowadays, to make digital twinning of existing assets more accessible. And a great part of it lies in better understanding the geometry of the captured data.
And I think that then leads on to my next question quite nicely, which is, you yourself have researched geometric digital twinning. And can you elaborate more on this and explain to us, for the novice, for example, what exactly is geometric digital twinning?
One of the systems of a digital twin is relevant to its geometry. And this is the geometric digital twin that my research work centers on as well. So imagine you're in a building and you laser scan it first with your preferred data capturing sensors, and this will create the so-called point cloud. This data is not perceived by our brains, even with color information. So it's really hard to understand what we're seeing. So in order to make this data meaningful, you feed 3D geometric representations on that data to better describe it. And this output is your geometric digital twin. So it is literally a twin of what you see in front of you, but in a virtual world.
And is this similar to the work that you recently authored for the paper called CLOI-NET, where you presented a novel class segmentation solution? Can you give us a bit more detail on what that research was about and what is its industrial significance for digital twinning?
First of all, I wanted to to define what CLOI-NET actually means. So it's like CLOI-NET. CLOI refers to the industrial object types that need automated modeling. Why would we need to define that in the first place? That's because if we think about an industrial factory, the number of industrial objects is very large, to the point where even the latest deep learning algorithms would not be able to process all of that at once. So an important step was first to understand which are the most important objects that need to be considered for automated modeling. And the first part of my research was early on to define those objects based on how frequently they appear in building information models and how much time it takes on average to create their 3D geometric representation. So these objects are what CLOI represents. So they are cylindrical objects, L shapes like angular steel shapes, C shapes, again in terms of steel, formats, I-beams, valves, flanges, and elbows in the piping system. And CLOI-NET is the first step in a two-step digital twinning framework of my PhD research. So these two steps are class and instance segmentation, as I call them, and they are widely used in the computer vision community. I'm going to give you some examples of what these processes mean. So both of them assign information to the point clouds that humans can understand. So for instance, if we laser scan a petrochemical plant and want to know where all the pipes of it are, then we would use class segmentation to give each 3D point an extra label, which represents the name of the physical object in a consistent format that humans can understand it. And that alone can be very helpful, especially for mechanical engineers or engineers in the field that want to know where all the pipelines are in the facility and generate 2D drawings from them, which they can correlate with other information such as piping and instrumentation diagrams. And it happens that usually facilities in the oil and gas industry are very well documented, but these documents are in many cases outdated. So with that as my main motivation, what this paper achieves is to automatically generate these class labels with laser scan point cloud data as input. And for cylinders, it improves the state-of-the-art practice. And for the rest of the objects, it's the first method actually to automatically segment them in industrial environments. So the methods discussed in the paper are data-driven and inspired by the latest advances in the computer vision community in terms of geometric processing of 3D point cloud data that I was talking at the beginning. And now, of course, the outputs of these methods cannot be 100% correct, meaning that there will always be cases where the designers and engineers would need to manually modify or correct the results. So another novelty of the method is to actually provide this trade-off between the class segmentation performance and manual annotation. So in other words, the human modelers can assist the class segmentation process by manually labeling a small subset of the facility, which is about 25 to 30% on average, and achieve optimal results. I also want to talk about the CLOI benchmark dataset that was created for the purposes of the validation of this work. So this was generated by a number of researchers at the University of Cambridge and myself using real point cloud datasets provided by Aviva and British Petroleum. And it is the only dataset of 4 real industrial data facilities available, fully labeled. So it is about 7 billion labeled 3D points that we manually generated.
Wow, that sounds like a lot of hard work to manually label that. So as you combine it with manual labeling together with your system, is it to improve its accuracy in detecting these types of objects? So it's akin to, as you said, a lot of the methods used in computer vision in other sectors, I would imagine as well. So I mean, it's quite exciting that these sorts of technologies are starting to also emerge in our sector. So from what you've seen so far, what has the success looked like with applying these systems? Is it still something that's being done at a research level, or are we seeing this technology already applied on real projects with real assets?
There are some successes already in the industry. I would say that, again, that's more for the design or new buildings, not so much on existing ones. And that's for two main reasons, I would say. Primarily because of the geometric digital twinning, which is what we were discussing before, is a manual process and takes so much time. So in the end, traditional methods are preferred, or the data is just not captured. What this means is that then we could not use the more advanced computer vision algorithms to generate these extra layers of information that can help the adoption and implementation of these methods to generate the digital twins more efficiently. So in order to be able to use those methods, we would need to create those large benchmark data sets for most of the assets that exist. And that would be the first step. And then the next step would be to have more efficient collaboration across fields, because even like let's say for an industrial facility, there are so many different end users and stakeholders from so many different perspectives that come into play that we would need to gather all the data requirements, having them into mind when designing this existing digital twin.
And of course, there are levels of maturity with the adoption of digital twinning in construction. So maybe you might be able to elaborate, what do these levels comprise of and look like, and how might this differ from more advanced sectors where digital twinning is already being implemented, at least at the manufacturing level?
I would refer to the levels of maturity in construction in two contexts. So first of all, in terms of what the digital twin should include, and then how much detailed this 3D representation would need to be. So in terms of the information that needs to be included, which would be like what are the objects that we need to have in the digital twin, we would usually use the term level of detail, or LOD, to describe the level of maturity of those digital twins. And for instance, I could use my research as an example that the outputs after applying those class and instance segmentation layers to it would be in the level of 300. But of course, we can refine that and bring it up to 500. And that depends again on the end user requirements and what the stakeholders of that facility would need to see. In terms of the other factor, the 3D representation, that can differ quite a lot from a very fine-grained representation where the twin would closely match the intricacies and peculiarities of a physical object, to a very, very coarse-grained representation that could be as generic as a simple cuboid. So again, it would greatly depend on the end user requirements of the project itself to specify those. And I would say that in the advanced manufacturing industry, these systems are indeed more mature, and there is a lot of great collaboration when using these tools, especially for software as a service SaaS products. So I will use the example of a PLM system where multiple multiple CAD models can be stored at different levels. So an analogy of that to illustrate the point would be if we think about an engineering bill of materials of a product, which includes the manufacturing components of it that as they were initially designed. So the as designed twin, let's say, in the building world. We could also have the manufacturing bill of materials, which would add additional relationships to it. When we assemble the product, that would be the as constructed twin in the building world. And we could also have the S-BOMs or the serviceable bill of materials, which would only include the parts that a service technician would need to service in that particular product configuration. And that could be our as-is condition in the building world. And of course, for just one product, we could have like multiple E-BOMs and M-BOMs and describing in so many different ways, like even just a slight differentiation of the color. In addition to that distinction that we just discussed, this goes to my second point on using SaaS PLM systems for each CAD model part itself, where we could have different states of the model and different revisions of that. And that can be constantly updated and reused in the SaaS scenario. And this is something that can be really valuable in the construction industry itself to adopt. I would also like to use the example of Onshape, which is a product we have at PTC that its value is on enforcing and endorsing the collaboration between designers and having those different updates and design stage for many stakeholders being in the same model.
And I would assume that even transitioning to what you described there into the SaaS models, it's not without its challenges, right? There will inevitably be things that are inhibiting or barriers that are making it more challenging for our sector to adopt these things. So from what you've seen within the infrastructure sector, what are some of these barriers that are particular to digital twinning?
Great question. And particularly, as we discussed before, that goes back into the time that is currently spent to generate those digital twins. So it's the BIM tools that we use require the personnel to be highly trained, and they need months, even years, for very complex assets to design them. And on top of that, another issue is that the greatest advantage that we see in other sectors, let's say in the automotive industry, for example, it's very easy for someone to label those data sets and use them thereafter for computer vision algorithms to get optimized performance. However, in our sector, without knowing exactly what these shapes are, what they represent, and knowing exactly the intricacies of each one, it would be very difficult to train someone who has not been in that facility, who doesn't have, let's say, the bridge engineering knowledge to know what each object is so that they can label it correctly. And if we don't have robust data sets as to run these algorithms, then of course we cannot make further advancements on that. So this is one of the barriers that I see in terms of generating these benchmarks that can help further develop the algorithms that are needed to generate geometric digital twins more efficiently. And the other one that I think is really important is to be able to invest more on larger and more consistent data collection between industry and academia. And this is, again, an area where autonomous vehicle industry has succeeded. And after the definition of a robust data set, then it comes to the adoption of the data-driven methods, which primarily for complex data like infrastructure assets will need to be deep learning based. And the last one, which I think that our industry can benefit from, is definitely from the manufacturing industry, since we would need to transition our BIM tools, and there have been some efforts there towards SaaS in a way that we can also communicate with PLM systems where necessary and available. And I think that could that would be a great way to endorse collaborative efforts.
Now, you mentioned in one of those barriers the reliance on manual labeling. Is it possible for us to overcome this by transitioning into methods that are unsupervised? So where we get to a stage that we no longer need this type of manual labeling, would that be the solution to overcome the issue?
That is definitely a direction, but that needs again like a small subset of labeled data. So in order to measure the performance and being able to compare it with what is actually the let's say the ground truth, the physical object in front of us. So there are methods that we can use, but again, it's a trade-off between how much of unlabeled data and what is the ratio of unlabeled versus labeled data that we can use in order to more effectively implement those algorithms.
And you also talk about the collaboration between our sector and, of course, computer science fields. And we've witnessed great steps of development so far, but it's not without also its challenges. So what are the things that you would hope would help collaboration between construction and the computer science field?
So I think that in order to engage stakeholders in these fields together in a way that both ends of the spectrum would benefit, the nature of the collaboration needs to be organic. So with that, I mean that both construction managers and leaders in the construction industry should speak the same language with computer scientists. It is often the case that this is passive engagement, where the direct benefits of investing in new algorithms for the generation of digital twins are not explicitly clear to either party, for example. And for this to happen effectively, the future leaders of the construction industry should start by first understanding some fundamental concepts that can facilitate collaboration, in my opinion. And that can be either through their education or in their professional communities, and especially in our days, like using all the online resources that we have available. So I think that small steps towards that direction can have a significant impact that can benefit both.
I think it's exciting, certainly the stage that we're at within the sector, certainly within the last 5 years alone. A lot more discussion is moving into areas like the research that you have been conducting so far. So I believe that there's still a lot more interesting collaborations that will perhaps create their own innovations in their own right. If we take the long-term view, what might the future hold for digital twins in construction? So if we try and project into the future, what are some of the things that you get excited about or that you're looking forward to seeing in our sector?
I think that our field will evolve rapidly, but after the first fundamental steps are taken. So with that, I would refer to having more effective data and code sharing of our research outputs. And there are, of course, some exceptions to the rule given the sensitivity of some of the data sources that we have in infrastructure assets. And if we think how laser scanners have evolved in the past decade, this is fascinating. Now we can even scan small rooms with our smartphones, let alone how many sensors for photogrammetry we have, and combined with laser scanning. In my view, what I would like to see, and where I think the greatest value for efficient and effective digital twinning adoption is the path towards automating the process as much as possible. Of course, with some sort of manual human interaction in the loop. And the metric for measuring that would be to reduce the modeling time so that digital twins can become more accessible in the construction industry.
That's great. And finally, where might our listeners find out more about the research that you've done in the past or what you're working on next?
So my website, my personal website, has links to my latest publications that our listeners can look into, and also they can look at my Google Scholar and ResearchGate for publications and preprints of my papers that are coming up next.
And just one last final question, which is, what sort of advice might you give to those in our industry seeking or exploring to invest into digital twin technologies and its implementation?
Yeah, that's a great one. So if in the construction industry, we start working hand in hand with companies in the technology sector so that adoption of the digital twin advancements can be easier. And there are already some steps that are taken towards defining data requirements that are needed for generating digital twins and infrastructure, but there is still, I think, a long way ahead. And this can also be done by small investments towards innovative initiatives within organizations, or also more organic relationships with academia for faster adoption of research and commercialization of that. So then if we think about the manufacturing industry, which went through 4 industrial revolutions so far towards automation, and it's still evolving, I think that the transition will take time, but if the right steps are taken, and there is a path forward towards a small but incremental innovative efforts, then I think that would be a smooth way ahead.
And finally, a heartfelt thank you to all of our followers who have been with us so far. If you enjoyed this episode, then please follow us on LinkedIn or YouTube, and better yet, share this episode with your friends and colleagues.